Mercury could have an 11-mile underground layer of diamonds, researchers say. A layer of diamonds up to 18 kilometers, 11 miles, thick could be tucked below the surface of Mercury, the solar system's smallest planet and the closest to the Sun, according to new research. The diamonds might have formed soon after Mercury itself coalesced into a planet about 4.5 billion years ago from a swirling cloud of dust and gas, in the crucible of a high-pressure, high-temperature environment. At this time, the fledgling planet is believed to have had a crust of graphite, floating over a deep magma ocean. A team of researchers recreated that searing environment in an experiment, with a machine called an anvil press that's normally used to study how materials behave under extreme pressure but also for the production of synthetic diamonds. The team inserted a synthetic mixture of elements, including silicon, titanium, magnesium and aluminum, inside a graphite capsule, mimicking the theorized composition of Mercury's interior in its early days. The researchers then subjected the capsule to pressures almost 70,000 times greater than those found on Earth's surface and temperatures up to 2,000 degrees Celsius, 3,630 degrees Fahrenheit, replicating the conditions likely found near Mercury's core billions of years ago. After the sample melted, the scientists looked at changes in the chemistry and minerals under an electron microscope and noted that the graphite had turned into diamond crystals. This mechanism, the researchers say, can not only give us more insight into the secrets hidden below Mercury's surface, but on planetary evolution and the internal structure of exoplanets with similar characteristics. Mysterious Mercury. Mercury is the second densest planet after Earth. A large metallic core takes up 85% of Mercury's radius, and it's also the least explored of the solar system's terrestrial planets. The last completed mission to Mercury, NASA's Messenger, orbited the planet between March 2011 and April 2015. Also known as the Mercury Surface, Space Environment, Geochemistry and Ranging Mission, it gathered data about the planet's geology, chemistry and magnetic field, before the spacecraft ran out of fuel and impacted the surface. We know there's a lot of carbon in the form of graphite on the surface of Mercury, but there are very few studies about the inside of the planet, said Yanhao Lin, a staff scientist at the Center for High-Pressure Science and Technology Advanced Research in Beijing and co-author of the study, which appeared in June in the journal Nature Communications. Compared to the Moon or Mars, we know very little about Mercury, also because we don't have any samples from the surface of the planet, Charlier said. Mercury is different from all the other terrestrial planets, he added, because it is so close to the Sun and therefore has a very low amount of oxygen, which affects its chemistry. One of Messenger's findings was the fact that Mercury is rich in carbon and its surface is gray due to the widespread presence of graphite, which is a form of carbon. Diamonds are also made of pure carbon, formed under specific pressure and temperature conditions. The researchers wanted to see whether this process could have played out during the planet's formation. When Lin, Charlier and their colleagues were preparing the experiment to mimic Mercury's interior shortly after the planet's formation, one crucial element was the knowledge that sulfur is also present on Mercury, as evidence from previous studies had shown. We found out that the conditions are different from Earth because there is a lot of sulfur on Mercury, which decreased the melting point of our sample, Charlier said. It fully melted at a lower temperature compared to a system without sulfur, which is good for the stability of diamond, because diamond likes high pressure but lower temperature. And this is mainly what our experiments tell us. The magma ocean of Mercury is cooler than expected, and also deeper as we know from the reinterpretation of geophysical measurements, he added, referring to data also from Messenger. These two factors, according to the study, are what makes the formation of diamonds possible. Diamonds on the surface? Charlier warns that the thickness of the diamond layer, between 15 and 18 kilometers, 9.3 and 11.1 miles, is only an estimate, and it might change because the process of formation of the diamonds is still ongoing as the core of Mercury continues to cool. It's also impossible to tell how large the individual diamonds may be. We have no clue about their size, but a diamond is made of carbon only, so they should be similar to what we know on Earth for their composition. They would look like pure diamonds, he said. Could the diamonds ever be mined? According to Charlier, that would be impossible even with future, more advanced technologies, because they are at a depth of about 500 kilometers, 310 miles. However, some lavas at the surface of Mercury have been formed by melting of the very deep mantle. It is reasonable to consider that this process is able to bring some diamonds to the surface, by analogy with what happens on Earth, he said. This diamond-forming process might be happening on some of the exoplanets that we are discovering in our galaxy, Charlier explained, if their chemistry is also low in oxygen like Mercury. If an exoplanet is smaller than Mercury, the core mantle boundary would be too shallow and the pressure would be too low, preventing the formation of the diamonds, he said. But a size between Mercury and Earth, combined with low oxygen, are favorable conditions to get diamonds. Scientists may know more soon. A mission called Bepicolombo, made up of 2 spacecraft launched in October 2018, is expected to conduct insertion into Mercury's orbit in December 2025 after performing a series of flybys. The mission, led by the European Space Agency and Japan Aerospace Exploration Agency, will study the planet from orbit and reveal much more about its interior and characteristics. The collaboration is named after an Italian scientist Giuseppe Bepi-Colombo, who invented the gravity assist maneuver routinely used to send probes to other planets. Bepi-Colombo can possibly identify and quantify the carbon on the surface, but also whether there is diamond on the surface or more graphite, Charlier said. This was not possible with Messenger, and the measurements will also be more precise, giving us better estimates of the depth of the core mantle boundary. We will be able to test our hypothesis again. An important step forward. Sean Solomon, the principal investigator for NASA's Messenger mission to Mercury and an adjunct senior research scientist at Columbia University in New York City, said it presents an interesting idea, but that it will be a challenge for future missions to Mercury to be able to confirm it. Any such diamond layer is deep and relatively thin, he said in an email. Solomon was not involved with the study. The most promising technique is probably seismology, because the velocities of seismic waves in diamond are much higher than those in mantle rocks or core material, but seismic measurements would require one or more long-lived landers on Mercury's surface, Solomon said. Bepi-Colombo, the only mission currently planned to reach Mercury, originally had a lander, but it was cut due to budget constraints. Felipe Gonzalez, a theoretical physicist at the Department of Earth and Planetary Science of the University of California, Berkeley, who was also not involved with the work, said the study represents an important step forward in our understanding of planetary interiors and how they form and evolve. He also believes that interdisciplinary studies like this one hold the key to address the complex problems that we face in science today. The proposed mechanism by which this diamond layer is formed is plausible, Gonzalez added, but it still largely depends on our assumptions about Mercury's interior. While very good constraints have been placed over the years as we study this planet more deeply, we can only approximate its composition in our models and experiments from indirect measurements, he said via email. Yet, this study still represents the best we can do with what we currently have, Gonzalez said. Only future missions to the planet Mercury will tell whether these predictions were correct. For now, we can focus on improving our understanding of materials at these extreme conditions by performing more and better simulations and experiments in our labs.